All right. Good morning, everybody. My name is Anders Heilsberg. I'm a technical fellow in the developer division at Microsoft, where I work as the chief architect of C#, but also oversee the development of all of our managed languages on .NET. And I'm here today to talk about future directions for C# and Visual Basic. Agenda, briefly. We're going to look at what's new in C# 5.0 and VB 11, which are the versions of the languages that are included in Visual Studio 11. We're going to take a look at writing asynchronous Metro-style applications, also hybrid C# JavaScript apps, and then a look into the future with a project we have called Roslyn. So we have a pretty long history now with our managed languages. In fact, I fondly remember the PDC of 2000 when we first introduced the world to managed code. That's 11 years ago. I can't believe it's been that long, really. And each of our language and .NET releases since have sort of had a theme to them. You know, the first one, yes, that was managed code and the rollout of .NET. Then generics, language integrated query in 2005, I think it was. The version of C# that's out there now was dynamic language support and parity between C# and VB, which is a theme that we are continuing. And today we're here to talk about the sort of two big things that are new in C# 5.0 and VB 11, which is support for the Windows runtime, which you've already seen a lot of, and asynchronous programming, which you've actually also seen a lot of. But we'll try to drill into it a little bit more in this talk here. Again here, just sort of summing up what the features are and sort of trying to hammer home here the parity, Windows runtime support, asynchronous programming. We also have a little extra feature that we managed to squeeze in called caller info attributes that I'll talk about. And then in VB 11, we're rounding out the parity between the languages by introducing iterators. So it's probably already obvious to you that asynchronous programming is becoming the norm in modern responsive applications. I'm actually surprised that there's barely a single talk here where people aren't talking about asynchronous programming. And of course, the reason asynchronous programming is important is that as we move to tablet form factors and touch, it is super important that the UI is very, very responsive. And asynchronous programming is probably one of the best ways of ensuring responsiveness in your UI. Instead of having operations where you call some method and then wait until the method returns to you, which could take a long time and therefore might frost over or spinning toilet bowls on your UI, if you use asynchronous programming, you instead initiate the operation and tell the operation what you want to continue with later as a callback. And in the interim, your app is free to do other stuff on the message loop. Alesh on the first day talked about how the sort of rule of thumb in designing the WinRT is that if an operation can take more than 50 milliseconds, it's going to be an asynchronous API. And I actually had one of my team members look through the entire sort of WinRT library code base there and look at how many of the entry points in there are asynchronous functions or methods. And it's somewhere between 10 and 15%, which may not seem high or may seem quite high, sort of depending on how you look. The thing that's interesting about it, though, is that those 10 and 15% tend to be the core operation, like the file I/O or the network I/O or whatever, where the rest of them tend to be like setting up properties and whatever. So pretty much no matter what you do in your WinRT application, you will be dealing with asynchrony. We have multiple ways of looking at asynchrony. Indeed, in .NET, we've had multiple. In the Windows runtime, asynchronous operations are represented with an interface called iasync operation of T. In the framework, we use the task of T class that was introduced in .NET 4.0. JavaScript uses promises. Common to all of them are that they are objects that represent ongoing operations. When you call an asynchronous API, you get back an object that represents the operation that you have started. And this object, you can ask for the status of the operation, you can ask it for the result when the operation is done, or you could, in certain cases, block and wait for the result. But you can also tell that object the callback that you would like to continue with when the operation is done. And that's sort of really the important part of asynchrony, is that things progress through callbacks instead of returning results. Now, the challenge with callbacks, however, is that they have a way of turning your code inside out. You know, you sort of gotta, like, right in the middle of your code, you gotta, like, turn the rest of your code into a lambda or a function, and if you have a loop, it gets really, like hair-maddeningly crazy to write this code. But an interesting insight is that it's actually possible to automatically transform normal code into callback style. Indeed, there's lots of research in computer science on continuation passing style programming, which is common in certain functional programming languages, and proof that any normal program can also be represented as a continuation style program. And that insight is what we leverage in the asynchronous programming support that we have in C# and VB. Indeed, asynchronous methods basically use the compiler to transform your normal code into a callback-based state machine. And that's what we're going to try to take a look at here. Here's an example of an asynchronous method. And really, if you look at it, it is an asynchronous method that gets some XML using an HTTP client. And you can read this method. It looks just like a regular old method. We create the client, we get a string or a response, and then we read the response as a string and parse it out as XML. But a couple of things sort of stand out. First, there's this async modifier that marks the method as async. And once you use that modifier, you are required in your method either to return void or to return some task of t, which you can see in our case here is an X element. The async modifier enables you then inside your method to await other asynchronous operations. And this is what I have an example of here. Now, the way this then works out is that when you hit this await operator, the compiler will actually at that point transform the rest of your method into a callback that it makes the continuation of the getAsync call. So basically, the transformation looks something like this. I've oversimplified here because there's more to it, exception handling and blah, blah, blah. But in principle, this is what happens. At the entry of the method, we allocate a task, or rather a factory of task, to represent the result of this method. And then we run up to the first await, as you can see. And then we continue. We make a lambda, in a sense, out of the rest of the code and attach that as the continuation onto the asynchronous operation that you're awaiting. And then you'll note that we immediately just return a task representing ourselves. And you'll see then that where the method on top had a return statement, we end up stuffing the result that you would want to return into the result of the task, which will then signal that task as complete, and then anyone who's waiting on that task will then run, and so on, and you can then get a whole sort of cascading effect that way. So let's try to look at this in action here. I'm going to switch to this machine here. There we go. And here I have a little app, that I've written, a Metro-style C# app. Let's just first run it so we can see what it does. It's a movie finder app that talks to Netflix's OData service and shows you a bunch of tiles that represent different queries for movies. I can, for example, click here and get myself all of the top-rated movies from the 80s, and then I can click on, here's one of my favorites, A Christmas Story with the Red Ryder carbine action 200-shot range model air rifle with et cetera, et cetera. I love that movie. It's, I can, of course, also go back and look at other categories, and you'll see that the UI of my app is actually responsive whilst I'm loading the movie titles here because it's all written asynchronously. So it's not like it frosts over while it's waiting for the result to come back. I can continue and do other things. So let's try to look at how this application is put together. In fact, let's try to start with the main page. And the first thing our main page does is it news up a data model. So the app is built using a view model that represents all of the data that we're looking at. And if we drill into the data model, that's actually where all the interesting stuff is. You see here all of my tiles that I was showing and the corresponding Netflix OData queries. And then you see that each of these groups has a list of movie groups. And a movie group in turn has title, status, blah, 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 blah. And ultimately down at the bottom, you know, it has a collection of movies. Now, if we look at how the app runs, when we run the main page, you'll see that we initialize the app. And then in here, after initializing the app, we then call, or sorry, no, let's actually look at what happens when we bring up one of the movie pages. So when I click on one of the categories, that brings up a movie list page. And in the movie list page, you'll see as we initialize here, that we have an async initialization method that calls into the data model and does a load movies async. And let's try to sort of follow the logic here. We call load movies async. That's the one that you saw that put up the loading ... It in turn calls our data feeds get movies async, which in turn, we're drilling in deeper and deeper, gets all the way down to this getString async method that fires off a query. Looks very similar to the little sample we looked at before. Now, one of the things that you note here is that these asynchronous methods compose just like normal methods. You know, you call asynchronous methods from asynchronous methods all the way down, in a sense. And now we're sort of down at the bottom here. The other thing that is interesting about asynchronous methods is that they don't start threads or anything like that. You know, they are just a way of composing asynchrony, you know, attaching code that you want to run before the asynchronous operation and after it completes. But the asynchrony itself, if you will, comes from sort of the lowest level function that I'm calling here called getAsync. That thing, in turn, arranges to, you know, set up an I/O completion port and fire off the HTTP request and then yields back to my app. And then at some point later, it completes and runs the continuation, so to speak. But it's interesting to think or to understand that asynchronous methods are about composing asynchrony, not about creating the asynchrony as such. It's more about orchestrating execution. Okay, so if we look at our code again here, we saw that when we run the app, that we have this loading ... and it sort of sits there for a while. And when we ask for a large query, you know, Netflix actually limits us to 500 at a time. And so, you know, first the experience is a little awkward, right? We're just sitting there looking at a blank screen. What if we instead were to batch up our requests and ask for 20 at a time, you know, because OData supports, you know, batching up like that. So let's try to see what it would look like to modify our app to do that. And so we'll go up to the load movies async method here, and then I'll change it a bit. Actually, what I'll do first is I will grab a piece of code called that I will insert down here that allows me to go query for the count of movies in a group simply by adding an inline count here to the OData query. And that just gives me back an int, or a task of int rather. And so now let's go up to the method here where we actually load the movies. And then let's modify that a bit. So we'll say var total count equals await data feed dot get movie count async of our query. So first, go get a count of the number of movies in the group. Then say count equals 0. Then we'll sit in a while loop here. So we'll make a loop out of it, and let's make the status text a little more interesting. We'll say string.format of 0 of 1 titles, and we'll show count, comma, total count, like that. Then we'll ask for a movie array, but this time we won't ask for all of them. We're going to ask for starting at count, and we'll ask for 20 at a time. And then we'll say if movie array dot length equals 0, then break. Then we're done. Otherwise, add them to our data-bound collection, and then increment count by the movie array dot length here. And then finally, at the bottom, we'll just update with the final count of movies that we read. So this looks like totally normal code that you would write, just a nice little while loop and so forth. And let's see what the effect of this is as we run. So here we are again, and then let's try to pick, let's say, documentaries here as a category. And now you see that immediately our UI is responsive, shows the first group, but it keeps just ticking away, and meanwhile I can just scroll, I can go look at what these movies are and so forth. And it's actually even better than that. I can start, let me get comedies also, let me get horror movies, let me get family adventures. And you'll see that the tiles just tick away, update, everything is still chugging along because I am asynchronous. And what I've actually done here is I have 4 or 3 load movies async methods going at the same time, interleaving with each other at all of the points where I'm awaiting asynchronous operations. That thing waits, and then one of the other guys completes a batch that gets to run on the UI thread, and they're all interleaving each other as they go along. Yet your code did not turn upside down. You get to just write it like normal code. Thank you. Let me just for kicks show you what it would look like to write this code without. Here's the manual one. It's actually going to blow off the screen here, but let me try to scroll back up. This is what it would look like to write the code without asynchronous methods. I'm not even going to try to make you understand it, but you see how I have to do a bunch of continue withs and then get the results out of that asynchrony. And then because I have a loop, I have to set up a lambda that I kick off down here for the first batch, and then when that completes, then I kick off the next batches, and my code is it runs down here and then up there and back and forth, and I don't even have error handling and exception handling in here, and trying to do that is just your head explodes. So the net effect is that people don't write code like this because it's too hard to make it work. And you can't see the forest for the trees, but now we've given you a tool that allows you to see the forest, so to speak, to concentrate on the algorithm. Just write your code like normal flow of control code, use all the statements that you're accustomed to, yet the code can execute asynchronously. Okay, back out of that. There. Now, one of the other things you might have noticed when I run the app here is that these group images come down sort of one at a time, tick, 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 tick. Now, let's go look at the logic that brings them down. That's actually kicked off by the main page, which calls this load group images async. That's the first thing it does when the app runs. And you can see I've cheated a little bit here. I've inserted a 2-second delay so we can observe this happening, because otherwise it would have just sort of all transpired while the startup screen was on. But so in here I have a little async method that first waits for 2 seconds, which just goes away, and then 2 seconds later it wakes up on the UI thread, and now it sits in a loop and loads each image asynchronously, and that's why you see them come down one at a time after each other. But if you think about it, these things are not dependent on each other. We could just load them all at the same time. We don't have to wait. This is asynchronous code. So I could instead write this code as follows. Let me put it in just so you can observe both of them. Here's the one at a time version. The next line here is do them all right now. So you see I have a little link query here. It's basically I'm calling load group image async for each of my movie groups. And that gives me a collection of tasks. Then I call task.whenAll, and I pass it that collection and say, please wait for all of them. and complete when they're all done. So if I put code here now, let me get rid of this guy. If I put code here, that code will run when all of the images have downloaded. But they all download in parallel. So asynchrony allows you to also run parallel code. So let's observe what happens now when the app comes up. Little delay, and then boom, they all arrive at the same time because they ran in parallel. All right. Thank you. So the fun thing here is I have not introduced any threading or concurrency in this app whatsoever. And so now you may wonder, well, when is threading appropriate? It's appropriate for situations where you have compute-intensive code. Let's say, for example, that I wanted to compute and sum up 2 billion square roots in a for loop. Well, that's going to take some time to do. If I were to do that on the UI thread, my app would frost over for a while, whilst it's grinding away. That's an example of where it's appropriate to put some work on a background thread. And then on the UI thread, you just want to wait for that to happen, like any other kind of asynchrony. Indeed, viewed from the outside, there's really no difference between work running on a background thread or an I/O completion port or whatever. It's an operation that you start, and then you wait for it, and when it's done, you then do something else. And so asynchronous programming allows you to view all of these things the same way. So let me try to insert some code here on the main page. You'll see that our main page calls that load group images async. Let me try to add a little compute stuff async method here. There we go. Scroll it up so you can see it. Here's a little method that computes 2 billion square roots and sums them up. Quite useless, but it takes a while. And because it takes a while, I want to run it on a background thread. And the way I run it on a background thread is I call task.run, and I give it a lambda to the piece of code. Now you'll notice, though, that I can still capture the sum variable that's sitting here as a local variable. And then I can simply await that asynchronously. So I'm just saying, get this started on a background thread, and when it completes, then do this down here. But meanwhile, UI thread is completely free to do whatever it wants to do. Let me try to insert a line of code here that kicks that off. And then let's try to run it. Let me first build it here, just so that's done. And then, actually, let me go back to and start up Task Manager, just so we can observe what happens. And I'll bring up the CPU monitor and park it down in the corner here. And then we'll try to run. And what we should see now is a plateau of CPU activity. Since this is a 4-core machine, it should be above 25%, pretty flat, because it's going to grind away on these square roots. But we'll try and run it, and then we'll see that the app actually is still quite responsive. So here we go. And I'm going to ask for some comedies. You can see they're ticking away. Meanwhile, my app is totally responsive, but you can see that it's grinding away on the square roots. And eventually, boom, there. Computed them, result shows up. But the app is totally responsive still because we've taken the compute-intensive work off of the UI thread and kept it going. OK, thank you. All right. OK, let me go back to the slides here. And sum up a little bit about asynchronous methods here. As you saw, they're marked with an async modifier. They must return task of t. You use the await keyword to cooperatively yield control, and asynchronous methods can then be resumed or are resumed when the awaited operation completes. The interesting thing is we actually do this await operator through a pattern. Anything that implements the appropriate, any object that implements the appropriate pattern of methods can be awaited. And that's the reason why you can both await task of t's and async operations, and you can even dream up your own things and await them if you so care to. These guys always execute in the synchronization context of their caller. I'm not going to drill in too deeply here, but it really means you always if you start on the UI thread, you continue on the UI thread. You're never hopping around on threads, which has traditionally been a problem with our asynchronous programming models. And finally, they feel just like good old synchronous code. You know, you can think of your code just the way you're supposed to think of your code. You don't have to think of the trees in the forest, so to speak. Okay, next thing I wanted to show was a little demo of C# and JavaScript interop. In fact, I'm going to go back to my demo box here, and we're going to load up a different project. And let's try to just run it, and you'll see that this is a very, very simple little JavaScript app that just views some items. And if we just sort of look at the structure of the app, you can see that it just makes up a fake item, makes a collection of them, and that's what it shows in a list view. Now, I'm going to show you how you can easily use C# as a compute engine or data access engine or whatever in this JavaScript app. In fact, I'm going to go to my project here, add a new project, and it's going to be a C# class library. We're going to call it Movie Finder. Okay, and that gives me a blank one with a class 1. We're just going to get rid of that one. And then instead, we're going to add an existing item. And we're going to go grab the code that we just wrote over in the other app, this data model file here. And here's the file that we were just looking at. I'm going to gut it out a little bit, this big complicated data model I had. I'm going to just simplify it a bit. There, get rid of all of that, and then we insert. But I'm going to keep the feed logic exactly the way it was and just put in here a simple data model instead. And you'll see here that I just have one method called getMoviesAsync or taskAsync that calls the same logic that we had before. And then I have a struct movie. And these, because my class is sealed and because my movies is declared as a struct, they will happily marshal using WinRT. Now, one thing though is this task type that I'm returning here is not a WinRT type. And so this is an example of one of the places where you kind of need to insert a little bridging method. So instead of exposing my task returning method, I can simply, let me just add a reference to that one. I can use iasync factory.create of my task returning method, and that turns it into an iasync operation, and then I can make this guy private instead. And that's pretty much it to get my C# code going. What I need to do, though, is I need to go change this project here to, instead of creating a class library, I want to create a WinMD file. And then finally, I want to, in my JavaScript project, I want to add a reference to my movie finder here, like that. And someone made this dialog very big. Luckily, I can use the close button. Okay, so now I have it sort of all set up. Let's try to just build and see that we happily build. We do. Now, what we want to do, though, is go actually try to use this code from JavaScript. And here, you see our code where we're creating our items. And we're going to change this now instead to use our data model and then download using C#. So we're going to declare var data model equals, and then we're going to say movie finder. And lo and behold, we get statement completion in JavaScript. The power of static typing. Because we do actually have type information for all of the, movie, let me just, finder dot, and in here you see data model. So, and then we can now say data model dot, and you'll see that we have getMoviesAsync again, because JavaScript, our JavaScript language service, is actually smart enough to know that, hey, I just made myself a data model and I didn't assign something else to it, so I actually get lucky here and get statement completion. So you sometimes get lucky in JavaScript. Of course, in C# you get lucky all the time. So but I'm just saying. Anyway, get movies async. Whoops. There we go. And then let's ask for catalog / genres of film noir / titles, like that. So now we've called our get movies async method, and then you'll note that this thing actually now has been turned into a JavaScript promise. So because it's gone from a task to an iasync operation in WinRT, and the JavaScript marshaller knows that, oh, iasync operations we surface as JavaScript promises. So I now get a then method that becomes my continuation that runs when the asynchronous operation completes. And in here, I can then say, make myself a function that, whoops, of movies. There. Indent all of this stuff. Close that one off. And now we just need to basically change this bit of logic here to instead map the return collections into a JavaScript array. And so we use movies.map, and then we map properties from the C# object into, I have box art URLs, and they become thumbnails instead in JavaScript. And that should do it. Let's try to run and see what happens. And here we go. JavaScript using C# asynchronously across using WinRT. OK. Let me get back to the slides here. So, caller info attributes. Think of this as the little palette cleanser in between the bigger demos here, if you will. This is a small feature that we managed to sneak into C#. In fact, it is not in the copy that you have in the developer preview, but it'll be in the final bits. A question we often get is, can we please have underbar file and line macros in C#? How many of you are familiar with what they do? A fair number. They're a C++ C preprocessor thing that basically gives you the name of the current source file and the line number, the current line number in the current source file. And they're useful for writing your own asserts and trace and diagnostic macros or functions and whatever. And people come to us pretty much all the time, ask, can we please have those because we want to do this, that, or the other tracing, debugging, diagnostic tool. And we go, well, we don't support macros in C#, and that's by design, and we don't really want to support macros. So how can we solve this problem? What we've done in C# instead of macros is that we've tried to leverage attributes. You, for example, know of the conditional compilation attribute that allows you to conditionally compile in a method. And the funny thing is, when we did that design, we actually thought about this problem, and we had a design worked up that would have worked if we had optional parameters. But we didn't have optional parameters originally in C#, so we didn't go implement it. But lo and behold, we now have optional parameters because we introduced those in C# 4.0. So now we've sort of revived this design that we actually did about 9 or 10 years ago. And it looks something like this. Let's say I wanted to write a trace utility with a writeLine method where I can insert trace.writelines in my code, and so I can follow diagnostically what's happening in my code. And what I really want this trace thing to be able to do is report to me what file number, file name, line number, and maybe even the name of the method or property or whatever that I was executing in. Well, what we've introduced in C# 5.0 and VB11 are 3 new attributes called caller file path, caller line number, and caller member name that you can put on an optional parameter. And if you do put that on an optional parameter, and if you omit that parameter in the call to the function, we will substitute the current file name or line number or member name instead of the default value that you had specified for the optional parameter. So, for example, if I have some code here where I say trace.writeLine of starting services, that gets turned into trace.writeLine of starting services and current file name, line number, and the member name of the member that called me. And of course, you can see how you can then, for example, compile that, combine that with a conditional attribute on your trace.write line, and now you get the same effect, and we've snuck it in without adding macros to the language. So, yeah. Thank you. Consider your palate cleansed. We'll move on here to something that's a little more forward-looking. We've talked about C# 5.0 VB11. I'm going to give you sort of a sneak peek of stuff that comes after that. I'm not going to say when we ship this because I don't know when we ship it, at least not in final form. But nonetheless, you've heard me over time talk about this compiler as a service thing. And we actually now have a project in earnest going to implement that, and we call it the Roslyn project, named after, have any of you ever seen the TV series Northern Exposure? It was filmed in a little town called Roslyn up in about an hour east of Seattle, cute little mining town. And so we picked that as the name for a project. And basically, in a nutshell, this project is about revising, reimagining what compilers do, if you will. Traditionally, a compiler is just sort of a black box. You know, in on one side, you feed it source files. Magic happens, and out the other end comes object files or assemblies or whatever the output format is. And internally, the compiler builds up a wealth of knowledge about the code that you fed it. And it applies that in producing its output, but then it promptly forgets everything that it knew. And that used to be just fine, you know, in the command line world, if you will. But we are increasingly addicted, if you will, to IDE productivity features like statement completion, refactoring, go to reference, find all references, go to definition, rename, blah, 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 blah. All of these things. And guess what? All of these things need all of the information that the compiler has. So this project is about opening up the compiler and making all of that information available as an API such that you can participate in building stuff that harnesses all of this knowledge. So you can do things like metaprogramming, REPL loops, you know, interactive use of the compiler, DSL embedding little snippets of C# and VB code in your domain-specific language and have it be compiled whenever you need it to compile, or, of course, having a full fidelity object model for the language that allows you to write your own refactorings in a very simple manner. So this project's been going now for a couple of years, and we've made a lot of progress, I'm happy to say. Basically, if you look at a compiler pipeline, what does a compiler pipeline look like internally? Well, compilers often look like this. You know, you have a parser lexer, you have a declaration phase in the compilation where you find all of the symbols that are being declared and you import all of the ones that are referenced from metadata. Then there's a binding phase where you bind all of the variables and methods, you know, all of the code in the method bodies to those declarations. And then finally there's an emit phase where you emit code, be it IL or object code. Now, this pipeline very much mirrors the set of APIs that we're building. So to represent the parser side, we have a syntax tree API, we have a symbol API, a binding and flow analysis API, and an emit API. We're currently building both a new C# and VB compilers. We're implementing them in C# and VB in managed code. And they all are built, they create these APIs, and we implement them in terms of themselves, if you will. The APIs are designed with modern design principles. For example, our syntax trees are completely immutable. So when you obtain a syntax tree, it is an immutable data structure. You can't change it. It's a snapshot, if you will. But you can make new syntax trees by reusing pieces from another syntax tree, and we are very efficient about doing that. And this gives us some tremendous advantages because this entire API is concurrency safe, for example, because there's no mutation possible. And that means you never end up in scary circumstances where you have a background compile going whilst the user is trying to do a refactoring and maybe they're banging on the same object graph, that would be a disaster. The APIs are also full fidelity, 100% fidelity. They can completely, like all the way down to the last character, represent a source file as a syntax tree. And if you call toString on the syntax tree, you get that same source file back. Bunch of other interesting stuff, error handling and so forth. But out of these APIs, we are also then building new language services that use them. For example, syntax trees are used in our colorizer, in our formatter. We use simple APIs for navigate to. All of our refactorings are built using, make also use of the binding and flow analysis API, and edit and continue makes use of the emit API. But the thing is, what we're doing here is we're dog fooding these very same APIs that we're making publicly available, and it'll be possible for anyone to slot into this and build their own refactorings, their own tools around all of this wealth of information. So today I'm happy to announce that, that we are releasing a CTP of all of this cool stuff. Thank you. It's actually not being released today. It's being released in 4 weeks, in the middle of October. But it's imminent, you know, and I've actually got a build of it here on my demo machine. And why don't we go take a look at what this stuff is all about. So let me switch to this one. Whoops. Hey, I'm not myself, apparently. There we go. There we go. Okay. So here I am in a little project where I have I've installed the Roslyn CTP on this machine, and I've added references to the Roslyn compilers and to the base compilers and to the C# compiler. All of this is available for both C# and VB, except for a few things that I'll call out. So I'm going to try to use one of the many APIs here to start with. I'm going to use the scripting services that are part of the compiler, because once you turn the compiler into an API that you can call at any point in time, well, you can also sort of use it in a script-like manner. So let me show you what that looks like. So I'm going to, well, actually, in the interest of not having you watch me type it all, I'm just going to grab a snippet here and paste it. In fact, let me borrow the mouse from this guy. There we go. So here, I knew up a script engine. If we drill in and look at what is this script engine, well, it derives from Common Script Engine. Let's look at what that is. And here you see that this guy has a whole API of abilities to compile code, compile submission, compile to a method, or execute a string of code and return me the object that represents the result of that. So let's try to play with that a little bit here, and we'll say engine.execute, and then the first thing we'll execute is using system, and we'll execute it with this current session as our context. A session is a thing that allows us to carry state forward between multiple submissions to the engine here. So then we'll do an engine.execute of for int I equals 0, I less than 10, I plus plus, console. We don't get statement completion in strings here, I'm sorry. So, whoops, semicolon there, comma, session. There we go. So, 2 lines of code. Let's try and run it and see what happens. And there you go. We compiled and ran code dynamically. Now, we can do other fun things. We could, for example, declare a method in here, square of x, that returns x times x, like that, and add that to our session, and then change our code here to do square of I instead. And let's try to run that and see that, yes, indeed, we get the same result. So we can define little methods, but we can do really crazy stuff too. Let me get rid of that, and then let me instead grab this piece of code here, paste it in. Here, space it out so you can see it a little bit. Scroll it up. Okay, so what I'm doing here is now I declare my function, then I execute a piece of code that returns a delegate to my function that I just created, and I return that out of the script engine into a local delegate here, which I then call through from a for loop. So now I'm actually calling code that doesn't even exist yet, but I'm making the code at runtime, and sure enough, that also works. In fact, you go, wow, you could make an interactive prompt out of this, couldn't you? So we've made an interactive prompt out of this. So if you go to other windows and C# interactive window, and we select that, up pops our interactive window that is part of the Roslyn CTP. And in here, you get to have a lot of fun. You can just type code and have it execute right there, math.sign. And oh, look at this, we got statement completion on our dynamically executing code here. What do you know? The power of static typing. I'm just saying, console.writeLine of hello world. It all works. Now, I've actually compiled or created myself a little file of snippets here that I can try to pick away at. Indeed, here's a little file just containing some C# code, and I can, in this edit window here, select code, and then I can just press Alt-Enter and have that code execute in the interactive window. So there, boom. Here's my little for loop running. Here's a definition of a, let me try to move this up a little, give us a little more room. Here's a definition of a function factorial with a doc comment on it and now I've actually in the interactive defined a factorial. So if I say fac of, you'll see that I get statement completion on the code that I just compiled with the documentation that I just put on it. Thank you. I can do Alt-up arrow here to go through my previous submissions, and I could actually here change my for loop to call factorial of I. You again see statement completion, everything, and here are like factorials of 0 to 10. Fun stuff. Let me add a print method. And now let me try to get all of the files in the Windows directory and print them. So I press Alt-Enter on this, and oops, it says directory doesn't exist in this context. Oh, well, because I don't have a using clause for wherever that guy is. I don't even remember where it is. But what I can do is just bring up that submission that I just had, and look how we get squigglies and we get refactorings in here too. So I can refactor my submission with a using IO and then press Enter, and now it works. Here's some other examples. Let's get me all of the processes running on this box, 83 of them. Let me find the biggest 5 offenders. Press Alt-Enter on that. There we go. Here's a link query. Give me the order by descending working set, select the process name, and take the top 5. And Devin comes out on top. Well, but you can really, truly just like slice and dice data in here. You know, load up some XML, you know, muck around in it to figure out, you know, what your data looks like. It's a wonderful tool for exploration. In fact, let me show you a few other fun things here. Let me go back to, whoops, let me down here, go pick up a few assembly references. We have a #R directive that you can use in the interactive that references other assemblies. So let me reference the WPF assemblies, and let me add a few more using clauses to my interactive session. And now, let me scroll down and try to do some fun stuff here. I'll make myself a window and make it topmost and show it. There we go. Now I have a window. I can move that guy around. All right. Let's put a background image in my window. Boom. There we go. Let's put a button in my window. There we go. Now we have a button. Let's add an event handler to the button. There. Now, this will use event syntax eventually. It doesn't in this particular build. But I can add an event handler that console.writeLines, and now when I click my button, I'm writing in the console window. So very, very, very dynamic. Okay, so that's a little glimpse of one of the good things that come out of turning a compiler into an API. And of course, I don't expect all of you to go write your own compilers or your own refactorings, but the fact that we put this out in the community makes it possible for someone to do it and share it, and I am sure someone will do things that we haven't even imagined with this stuff. So let's get rid of our window here, w.close. Poof. And let's get rid of the interactive window. Okay, a couple of other things that are made possible by this Roslyn stuff is user-written refactorings. Let me try to illustrate that with let's say I have a little class called product. And let's say that I now want this thing to be data bindable, which means I have to implement iNotify property change. And of course, I can use the IDEs, iNotify. I can use the IDE to help me implement, but if I do, all it does is add an event. But that event is never going to fire unless I go write some code on every property that sets off this property notify change. So that's not super useful. And this is sort of an example of where, hey, how about having a refactoring that allows me to select some properties and then say, make them property notifiable. And I can simply do that. And this is a refactoring that was implemented using Roslyn, where it now implements iProperty notified for me, puts the appropriate code in each of the properties, adds a setProperty method, and adds the event handler. But it's not just a dumb code generator. If I were to add yet another property like units in stock, for example, let me select that guy. I can just say, well, make this data bindable. It introduces a field, it adds the appropriate code, but it doesn't go spew out yet another setProperty method. It understands the code and does the right thing to the code. It'll modify my using clauses, et cetera, if I don't have to write using clauses. So let's try to look at what does it look like to build one of these refactorings using the Roslyn APIs. And I can't show you all of the code here, so all I'm going to do is show you a few of the little snippets of it that are interesting. One of them is, for example, the method that determines whether this refactoring is currently available. The way that is implemented is we get presented with a syntax tree for the code that you're in. We ask for a compilation for that, then we ask for the semantic model so we can ask things about symbols. And then we say, get me all of the descendant nodes within this text span of type property declaration syntax where, and then I have an is expandable property helper method that I'm calling here. So I can write a little link query here over my code, to determine whether this thing applies. Now, in order to actually do the refactoring or the code generation, we have a property rewriter, if we drill into that. This is actually a visitor that you could use over syntax trees, and in this particular one here, we visit all property declarations and we visit type declarations to do things. And here's, for example, the place where we implement property notified changed. If I go look at that, you'll see in here that here is, for example, an example of the code that determines whether we should inject a setProperty method into the code. And it says, hey, is there a member setProperty that is a method that has 3 parameters and 1 type parameter? And if not, then go generate it. So we can ask these intelligent questions, but we're not just seeing if there's something in there called setProperty, because the user might have written something themselves. And in order to generate the setProperty guy, this is an interesting use here of, we call syntax.parse statement, and then we just have some C# code, and poof, that gives us a syntax tree. And now we can take the syntax tree and manipulate it around to what we really want, and then we can jam that into by two-string it, so to speak. So we get all these nice tools to manipulate code in an intelligent manner. Thank you. All right, just for kicks, let me go back to the code that I just had here. I'll just get rid of all of this property stuff again and just get back to where we were with our little program. So I mentioned that we have object models for both C# and VB languages, and you know, a fun thing you can do with that is you can convert from one to the other, you know, with full fidelity. So let me show you a neat little extension that the Roslyn APIs also include. I'm just going to select all of this C# code, and then I'm going to open myself a VB project. Yeah, save the changes to that. Here. Let's just gut out this code, and then let's take what's on the clipboard and paste it as Visual Basic here. And poof. And here we get all that same code. And you'll note that it understands that, you know, a cast in VB is direct cast of func of integer, whatever. I personally wouldn't have been able to write this code, but it's no, I'm not. But hey, this stuff works actually. Let me try and run it. And there you see Visual Basic using the C# compiler to compile C# code in little snippets. In fact, we could take the snippets out of quotes here. Let's select our little square function. And then why don't we paste that as Visual Basic? Poof, there's our little square function as VB. And hey, let's take all of this stuff, and then let's go back to C#. Let's get rid of all of this, and then let's paste that as C# instead. And now we go the other way, back and forth. Now, you'll note that things changed a little bit. I used to have a for loop, and now I ended up with a while statement. You know, this is not the final thing. But hey, it does the same thing. But you know, C# and VB's for statements aren't quite the same, so this translator translates them a little bit differently. Now, let's just look at, you know, again, all I can do is show you a glimpse of this source code, but I'll do that. Here's the converter. You'll see this is a project or a solution that has two projects in it, and we're going to give you source code to all of this stuff. So these are just samples, basically, that we provide. There's a C# to Visual Basic converter written in C#. There's a Visual Basic to C# converter written in VB. Of course, you could just copy and paste and make one. But we didn't do that by copy and pasting. But here you see, at the top of it, really, we use both compilers in the same project. We use a using alias. Here's the C# compiler and the VB compiler. And then in the converter, we take a C# syntax tree and return a VB syntax node. And in there, we simply iterate over the tree using a visitor. Okay, there's some code in there, but you know, it's actually understandable code if you have time to look at it. And the VB converter, it's the same, you know, but in VB. Okay, so that's sort of a glimpse of what you can do with Roslyn. Let me just go back and do a little bit of summarizing here. I should mention that in the CTP, the C# interactive prompt that you saw me demo is going to be available for C# in the CTP. We're working on the VB one, but it's not going to be included in the first CTP that we release. It will be there later. It's just a matter of staging the work, because we're also got this Win8 thing that we got to do. So in summary, I think, and honestly, you know, from the conference, you have seen how C# and VB deeply support the Windows runtimes. These are first-class languages in the Windows ecosystem. C# and VB make asynchronous programming easy. And I'll add a little plug here, actually. You know, a lot of the asynchronous work that we're doing in C# and VB first saw the light of day in a language called F#. And you know, F# also was a big inspiration for us in all of the functional programming stuff that we've done. We've not talked a lot about F# at the conference, but Don has a talk tomorrow, so if you get a chance to go see that. You saw how it's easy to create hybrid C# VB and JavaScript apps using the Windows runtime. And finally, we'll have the Roslyn CTP available soon, i.e. in a month. And that is it for me today. I thank you for coming. I hope you enjoy the rest of the conference and give us feedback. Thank you. Thank you. Thanks.